students, now the topic from electrochemistry session 2. What are the learning objectives in this chapter? Second session, factors affecting equivalent conductance, measurement of conductivity of ionic solutions, conductivity calculation, and problem. One example problem. Okay. Now, factors affecting electrolytic conductance. What are the factors? Number 1, if the inter-ionic attraction between the oppositively charged ions of solutes increases, the conductance will decrease. Inter-ionic attraction means the positive charged ions are surrounded with negative ions, negative charged ions surrounded with positive charged ions. The attraction between the oppositive charged ions in solutes increases. Now that type of attraction increases in the solute, the conductance will decrease. This is the affecting main reason for this in solution. Next, second point, solvent of high dielectric constant, so high conductance in solution. Solvent of higher dielectric constant. Solvent in solution, which solvent have the higher dielectric constant? It has the higher conductance in solution. Next, conductance is inversely proportional to the viscosity of the medium. Viscosity of the medium means thickness of the liquid. Thickness of the liquid is higher, viscosity is higher, then the conductivity decrease. More dilution give the more conductance. This is the reason. Okay. Now, next, if the temperature of the electrolytic solution increases, when temperature increases the solution, the conductance also increases, because the movement of ions is fast. Okay. Increase in temperature increases the kinetic energy. This is the reason. Kinetic energy of the ions are increases. Decrease the attractive forces between the oppositely charged. Already first point, the oppositely charged ion attraction is affected. So attractive force between the oppositely charged ions, and hence conductivity increases. Because the temperature increases means the movement of ions across the distance is increases. So conductance will increase. Okay. Fourth point. Fifth point, molar conductance of the solution increases. Molar conductance of the solution increases with the increase in dilution. More dilute, molar conductance of the solution increases. Because strong electrolyte, intra-ionic forces of attraction decrease the dilution. Already first point, again and again, the first point is more important. Strong electrolyte, intra-ionic forces of attraction decreases with dilution. Weak electrolyte, degree of dissociation increases with dilution. Degree of dissociation increases. Already last chapter we saw that the weak electrolyte, degree of dissociation increases with dilution. Okay. Next, example problem. Example problem is the solution for that I will explain to you. A conductivity cell has two platinum electrodes, positive and negative electrodes, separated by the distance 1.5 centimeter. 1.5 centimeter distance, keep the distance between them, and cross-sectional of the area of the electrodes are 4.5 square centimeter. Using this cell, The resistance of the electrolyte, normality of the electrolyte 0.5 normality, 0.5 normal. The measured as 15 ohm. This is the resistance of the electrolytic solution. So what is the specific conductance? That is kappa. Kappa, the letter is kappa. You find out the kappa. Okay. Now the solution I will explain to you. Now in this problem we give the data, write the data. L is equal to 1.5 centimeter, 1.5 centimeter you converted to meter, okay. 1.5 divided by 100, divided by 100, that is 1.5 into 10 to the power of minus 2 meter, okay. Next, A, cross sectional area A of the electrode is equal to 4.5 centimeter cube. Centimeter cube means square centimeter means centimeter cube, square, 4.5 centimeter square. 4.5 centimeter square I want to convert it to meter square. So again 4.5 divided by 100 divided by 100 into 100, 100 into 100, because square, centimeter square is there, therefore 10 to the power of minus 2 into 10 to the power of minus 2, 10 to the power of minus 4 meter square, okay. 4.5 divided by 100 into 100, okay, that is the value for 10 to the power of minus 4, okay. Now next, resistance of the electrolyte. Resistance of the electrolyte means 15 ohm. Now the formula, kappa is equal to 1 by R 1 by L by A, 1 by R into L by A. This is the formula. Substitute this 1 by 15 ohm into 1.5 into 10 to the power of minus 2 meter divided by 4.5 into 10 to the power of minus 4 meter square. Now full elaborate calculation I will give that. Now 1 by 15 into 1.5 into divided by 4.5 into 10 to the power of minus 2 divided by 10 to the power of minus 4. The given units are I write it separately, okay. Meter divided by ohm meter square, okay. Now 1 by 15 into 1.5 divided by 4.5, I remove the point into 10 by divided by 10 into 10 to the power of minus 2 divided by minus 4. Cancel the meter square, again ohm per 1, meter per 1. So 1 by 15 into 15 divided by 45 into 10 to the power of plus again denominator to go to the bring to the numerator. So 10 to the power of 2, minus 2 and plus 4 is 2. So 1 by 15 cancelled, 1 by 45 into 10 to the power of square. Therefore 1 by 45 is 10 square means 100 divided by 45 sm per 1. This is equal to 2.22 sm per 1. This is the final answer, okay. Now next problem. Calculate the molar conductance of 0.025 mole aqueous solution of calcium chloride at 25 degrees centigrade. That is, molar conductance means kappa. Kappa is equal to kappa. I want to calculate the kappa. So 0.025 mole concentration of the solution, and calcium chloride, concentration of the calcium chloride solution. The specific conductance of the electricity, conductance of the calcium chloride is 12.04 into 10 to the power of minus 2 sm per minus 1. So molar conductance formula, lambda m is equal to kappa into 10 to the power of minus 3 divided by m. M means M means that is concentration, molar concentration. Okay. Now kappa value is already given that the specific conductance of the calcium chloride 12.04 into 10 to the power of minus 2 Sm power minus 1 into 10 minus 3 divided by 10 to the power of minus 3 mole per 1 meter cube, mole per 1 meter cube. Okay. Now divided by 0.025 concentration of the solution. Okay. Now make the calculation. Details of the calculation I will separate. Detail 12.04 into 10 to the power of minus 2 into 10 to the power of minus 3 divided by 0.025 unit separate, write the separately S meter per 1 mole per 1 meter cube. So 12.04 into 10 to the power of minus 3 minus 2 10 to the power of minus 5. Again I want to remove the 0.4 the denominator 0.025. I remove the 3 place decimal place. So 1000 multiplied by 1000. I also multiply in numerator. Numerator 1000, denominator 1000. So 1040 divided by 25 into 10 to the power of minus 5. The meter per 1 again the meter cube power deduct the power. Okay. Now I divide the 1040 divided by 25. This is the answer 481.6 into 10 to the power of minus 5 Sm meter square mole per 1. This is the final answer. Okay. Final answer of the problem is 481.6 into 10 to the power minus 5 Sm square mole per 1. So next, measurement of the conductivity of ionic solution. What are the measurement of the ionic solution methods? We have already learned to measure the specific resistance of metallic wire using meter bridge in physics practical experiment. Already know that specific resistance of the metallic wire using meter bridge practical. Okay. Next, it works of the principle of Wheatstone bridge. The principle of Wheatstone is in theory. Okay. Similarly, the conductivity of electrolytic solution. Electrolytic solution also determined by using Wheatstone bridge. Wheatstone bridge arrangement of the one resistance is replaced by a conductivity cell filled with the electrolytic solution of unknown conductivity. This is the point. Unknown solution we filled with the conductivity cell. Okay. Understand? Wheatstone bridge arrangement using one resistance is replaced by the conductivity cell filled with the electrolytic solution. We see the picture and you will understand. In the measurement of the specific resistance, the DC power supply is used. DC power, not AC power. So the measurement of specific resistance of metallic wire, DC power is used. Okay. Now the image using Wheatstone bridge. Okay. In this image, the conductivity cell. This is the conductivity cell, and then this is the water thermostat. Water thermostat means the conductance of the heat is without conductance of the heat, the water thermostat. And then this is the electric solution inside the tube, inside the test tube. Inside the test tube, electrolytic solution. Resistance R unknown solution. One resistance is removed with enclose the resistance of Wheatstone bridge, okay. Now AC source is there. This is the diagram for conductivity cell, water thermostat, electrolytic solution. This is the electrolytic solution for the measurement of want to measure the resistance of the solution, okay. Here if you supply the DC current through the conductivity cell, it will lead to the electrolysis of the taken in the cell. DC current is used to is not able to use, because this is the reason, this is underline it, because this is one more question. AC current is used, not for DC. Why DC is not used? Because if the DC current conductivity cell is used, it leads to electrolysis of the solution. It take the electrolysis of the solution, undergo the electrolysis of the solution, okay. So not used. AC current is used for prevent the electrolysis. This is the important one more question, okay. Now the Wheatstone bridge is constituted using known resistances P, Q, a variable resistance S, and conductivity cell resistance, let the resistance of the electrolytic solution taken is by R. This is the unknown resistance, and then PQ is the known resistance, S is the variable resistance S. So this is the connection between the unknown electrolytic solution. Now the AC source 550 Hz to 5 kHz is connected between the junction A and C, A and C end connected with the AC source. Connect the suitable detector E such that telephone earpiece detector between the junctions B and D. The E is connected. This is the detector. Detector means like a telephone earpiece detector, okay. This is the between the B and D. Now the variable resistance S is adjusted till the bridge is balanced. The Wheatstone bridge adjustment is in the S resistance. This is the variable resistance. Now the relationship in Wheatstone bridge, B by Q is equal to R by S. This is the relationship. So I want R shift the S to the left side. So P by Q into S. This is the relationship. In this relationship, the resistance of the electrolytic solution R is calculated from the known resistance values P, Q and S under balanced condition. From using this relationship P by Q is equal to R by S, we find the unknown resistance of the solution. Now conductivity calculation. Conductivity calculation specific conductance or conductivity of the electrolyte can be calculated from the resistance value using following expression. What is the formula? The formula is kappa is equal to 1 by R L by A. 1 by R is the R is the resistance, L is the cross section distance between the electrodes, A is the cross sectional area. Now we calculate the specific conductance of the electrolyte. The value of the constant, cell constant L by A is usually provided by the cell manufacturer. In this known value L by A is already provided by the cell manufacturer. Alternatively, cell constant may be determined using potassium chloride solution whose the concentration and specific conductance are known. If not available means you use the potassium chloride solution and determined the specific contents of the solution. Okay. Now problem. Now the problem, I will show the book. Okay. This is the problem. The resistance of a conductivity cell is measured as 190 ohm using 0.1 mole potassium chloride solution. Specific conductance of potassium chloride is 0.1 mole. Mole of potassium chloride is 1.3 Sm power 1. This is the specific conductance of the potassium chloride solution in 0.1 mole normality. So this is a known value for potassium chloride solution. When the same cell is filled with 0.003 mole sodium chloride solution. Sodium chloride solution measured the resistance 6.3 kilo ohm. The sodium chloride solution's resistance is 6.3 kilo ohm. The measurements are made particular temperature. Calculate the specific molar conductance of the sodium chloride solution. We want the specific molar conductance of the sodium chloride solution. What are the data? Given data, kappa value of the solution. Kappa value is 1.3. The potassium chloride. Kappa value for the potassium chloride solution 1.3 into 1.3 Sm power minus 1. So next, resistance of the solution 190 ohm of the potassium chloride solution. This is the given data. Next, additional data, concentration of the potassium chloride solution 0.1 mole. Concentration of the potassium chloride is 0.1 mole and concentration of the sodium chloride solution is 0.003 mole. Okay, resistance of the NaCl, sodium chloride of the resistance 6.3 ohm. Okay, these are the again extra data for this. Now kappa value is equal to 1 by R into L by A. This is the formula. So we find the L by A value is equal to K into R. The R is bring left side on numerator. Okay. So K kappa into R is equal to 1.3 Sm power minus 1, 190 ohm. Okay. Now the unit S is cancelled, ohm is cancelled because ohm is reciprocal ohm. Reciprocal ohm value is S. So 1.3 into 190, the value is 247 meter per 1. 247 per meter 1. Okay, this is the value. Next, kappa value is equal to kappa value for NaCl. Kappa specific conductance. We want that this is the formula. 1 by R NaCl L by A. Therefore, 1 by 6.3 kilo ohm. Already given the resistance value of the sodium chloride 6.3 kilo ohm into L by A already find out 247 is equal to 247 divided by 6.3 into 10 into 10 because the 0.3 removal of 0.3 in denominator. So 247 into 10 divided by 6.3 into 10 into 10 to already 10 to the kilo ohm. Kilo ohm means 1000 ohm. 1000 ohm. So you multiply the 1000 ohm. So the value is 247 into 10 2470 divided by 63 into 10 to the power of minus the 3 is bring the numerator, so minus 3 meter per 1 and ohm per 1. So 39, I divide the 2470 divided by 63, this method. Okay, 39.2 into 10 to the power of minus 3 Sm power minus 1. Okay, understand? The ohm per 1 is changed to S power. Okay, now lambda m is equal to kappa into 10 to the power of 3 mole per 1 m cube divided by m. Lambda m we want specific conductance. Okay, molar specific conductance. Okay, 39.2 kappa value already find out that 39.2. This is the kappa value. 10 to the power of minus 3 Sm power minus 1 into 10 to the minus 3 mole per 1 meter cube divided by 0.003 molar value of the sodium chloride solution. Mole value, that concentration of the solution 0.03. So again 39.2 into 10 to the power of 6 minus 3 into minus 3 minus 6 divided by 0.003 unit. Already write it, Sm power minus 1 mole per 1 meter squared. So this is the value. I already make a 003 is round of that 1000, numerator multiply by 1000 and denominator multiply by 1000. So 39.2 into 1000 divided by 0.003 into 1000 into 10 to the power of minus 6, cancel, power minus 1 square, so Sm square mole per 1. So 39.3 into 10 to the power of square, square means 100. I want to, here 100 is there, so 100 into 10 to the power of minus 6 Sm. The value is 13.04 into 10 to the power of 3. Here I make the calculation. The calculation is 130.6 into 10 to the power of minus 4, 130.6 divided by 10 into 10 to the power of minus 3. 1 is here, I write in denominator, that about 130.6 into 10 to the power of minus 3 divided by 10. So the lambda m is equal to 13.06 into 10 to the power of 3 Sm square mole per. This is the final answer in this problem. Okay.